Yes, welcome you all for another session on vibrations, undamped free vibrations of single degree freedom system analysis by energy method. Okay, we have discussed the analysis methods by Newton's second law and D'Alembert's principle. Okay, I shall explain what is energy method and then we shall employ or we shall apply energy method for the same two problems which we have done it by Newton's second law and D'Alembert's principle. Okay, what is energy method? So energy method is based on the law of conservation of energy. So what is the last statement of the law of conservation of energy? We all know that the total energy at any time is a constant. Sorry, that is the ultimate, that's how we apply it. Energy neither can be created nor destroyed. At the most it can be converted from one form to another. Okay, the same thing when we apply to our system, we say that the total energy is the sum of the energies in different forms. Okay, that is constant and that is not going to change. Okay, since the system is undamped system, there is no loss of energy and therefore the energy may be in different forms but there is no loss of energy. So though the energy may exist in various forms like chemical energy, electrical energy, magnetic energy, etc., we call it so many forms, but for our systems, mechanical systems, we are going to have only two forms of energy here, either kinetic energy or potential energy. Kinetic energy is basically the energy possessed by a body due to its motion. Okay, because of the motion, whatever the energy is possessed, that energy we call it as kinetic energy. And similarly, the potential energy, which may be because of the two things, etc., I shall tell it. Okay, then I know that total energy. So in short, I call it as TE. TE is the total energy. Okay, this is the sum of what? Kinetic energy plus potential energy. So kinetic energy, many times loosely we call it as mechanical energy. Okay, so whenever we say mechanical energy, it is basically kinetic energy what we are talking. Kinetic energy is the energy possessed by the body because of its motion. Okay, kinetic energy, okay, when I say motion, due to motion, I have two types of motion. Motion along a straight line, that we call it as translation, or motion along basically a straight line. So therefore, in a system, I am talking not about this system, in general, the systems, mechanical systems, there may be some parts which may be undergoing motion along a straight line, horizontally, vertically, or any inclined position. They are moving along a straight line. So that line, that energy, kinetic energy, because of translation. Okay, it is basically kinetic energy, TRA means kinetic energy possessed by the bodies which are moving along the straight line. Okay, then there may be certain bodies which may be undergoing rotation. So therefore, I may have kinetic energy because of rotation. So these two together will give us what is the total kinetic energy in the system. Similarly, the potential energy, there are two forms, two ways, potential energy due to position of the body. Okay, so you know that, say if I have, imagine I have a small stone here, okay, say a dust like this. Okay, this, the position of this body with respect to the center of the earth. Okay, as the body goes away from the center of the earth, then its potential energy is increasing. If the body comes closer to the center of the earth, then its potential energy is decreasing. If it goes and imagine it at the center of the earth, then its potential energy is zero. Okay, the position means the position of the body with respect to the center of the earth. Okay, then the body is having, you can easily feel it also. So imagine, hold a hand like this, you allow this small stone or duster from a height, say 1 foot, something like this. Then you allow it. Then you increase this, go on increasing this length. Then imagine falling it from a certain height, say meters together, and you hold it in your hand, and all the energy possessed by it, that has to be absorbed by your hand. So probably if it is falling from far height, probably you may not have your hand like this, probably you will take it. Because as the energy possessed by this same mass is not changing, and it is only the position which is changing, and that will make the energy. Okay, so how to calculate, etc. In the next step I am going to come there. Potential energy due to position of the spring. Okay, this. Then I also have what's called as, whenever you have springs, now, and the springs will store energy. And I shall demonstrate how that, you know that. So if you compress the spring and you allow it, the moment you remove it, then suddenly jumps now because of the energy. There is energy stored in the spring, and that energy is also called as the potential energy. Potential energy in the spring. So this is another way of storing, having what is called as potential energy. These two are kinetic energies, and these two are potential energies. Now let me calculate how to calculate kinetic energy of a body which is moving along a straight line. Okay, imagine that you have a mass, and this mass is moving along a straight line, say horizontal, and say its velocity is x dot. Okay, then you know already, you are quite familiar, the kinetic energy is half m into x dot square. Half mv square. V is nothing but the velocity. Velocity is nothing but x dot dx by dt. So half mx dot square, that will give you the kinetic energy because of translatory motion. So similarly, kinetic energy because of rotation. You have a disc-like thing, and this is rotating, say about at an angular velocity of omega, and I is the moment of inertia of this body about this. In that case, it is very similar to half m into half as it is. Instead of m, I have I, and instead of x dot, linear velocity, I have what is called as theta dot, the angular velocity, theta dot square. Half I into theta dot square will give us what is the kinetic energy because of rotation. So I is the moment of inertia of this body about which the rotation is taking place. If the same body is rotating about, say, this point, it is rotating. In that case, I have to take the moment of inertia of this about this point. Please remember, I is the moment of inertia of the body about which the rotation is taking place. That is very, very important all the time. Okay, then potential energy because of the position. Okay, suppose the mass, say m is here. Say, let me call this as the equilibrium position. So here we are not interested in the absolute potential energy. We are interested in the change in the potential energy with respect to the equilibrium position. Say it is in the equilibrium position, and say mass has come here. Say mass has come to this position, and say this distance is what is h. Okay, with respect to the center of the center of the earth is down only, so it has come. With respect to the equilibrium position, the mass has gone away from the center of the earth. Therefore, its potential energy has increased. So the potential energy here minus the potential energy here. Okay, this, if I say this is equal to m into g, as it is mgh. So it is plus mgh, meaning that the potential energy has increased. And the same mass with respect to the equilibrium position, say it has come to this position. So let me assume that this distance is, say, h1. So first of all, with respect to the equilibrium position, the mass has come closer to the Earth center. Therefore, its potential energy has decreased. So therefore, I shall start with minus. So minus mg into h1. This is how we calculate the potential energy. So with respect to the equilibrium position, if its height has increased, then we say that potential energy is positive. And how much is that? Mg multiplied by what is the change in the height. Okay? Or if it has gone closer to the Earth center, then we say that its potential energy change is minus, or in other words, meaning that its potential energy has decreased with respect to its equilibrium position, and therefore it is this. So this is how we calculate the potential energy due to the change in the position of the mass. Okay, then how to calculate the spring, the energy stored in the spring. Okay, the energy stored in the spring state. See, I have some force here, F1. I have already some force. Or in other words, let me demonstrate in the same way we normally come across. See, this is the spring, and right now there is no load acting on it. This is what is called as the free length of the spring. The length of the spring is free length. Height measured. The length measured along the axis of the spring. Okay. When there is no load, that is called as free length. Okay. Now I am going to attach one mass here. Okay. This is mass, and the same thing. So the mass will come to this position. I shall remove this mass. The mass will occupy this position. And I know that, say, this is the equilibrium position, and this distance I have called it as delta St. So what is the spring force? What is the force on the spring, or what is the spring force at this position? That is nothing but K multiplied by delta St. Stiffness multiplied by the elongation, that will give you what is the force acting on the spring. Okay, so now suppose the mass further undergoes some more displacement. Okay, m is here, and let me assume that this is the further displacement. I want to know what is the energy stored in this during this time. What is potential energy? That is nothing but the energy stored in the spring. So as we all know that the force on the spring depends upon what is the elongation of the spring. So right now the spring has undergone an elongation of delta St. Therefore the force on the spring is K into delta St. At this position, what is the force? Force on the spring, that is K into delta St. Okay, so in this position, what is the force on the spring? Okay, that is also Ka multiplied by what is the extension of the spring? It is delta St plus x. So now K into delta St plus x. So if the spring is somewhere here, or the mass is somewhere here, then the spring force is different. K multiplied by whatever this distance plus delta St. What I mean is, the force on the spring is continuously changing from here up to here. It is continuously changing. And during this time, there is displacement. The displacement is x. But the force is continuously changing. The force multiplied by displacement. Force multiplied by displacement is nothing but the work done, and that is nothing but the energy. Okay, force multiplied by displacement, that is what I want to do. But what force should I take? The force is here at this position is K delta St. The force by the time it reaches the new position, it becomes K into delta St plus x. If it is somewhere here, the force is different. The force is continuously changing. Then what force should I take and multiply it by displacement to get the energy? That force is nothing but the average force. The average force during this time multiplied by displacement. Multiplied by displacement. What is the average force? The average force during this time is K into delta St plus K times delta St plus X. This divided by 2. This is the average force. Multiplied by what is the displacement? What is the displacement? The displacement is X. So this is the energy stored in the spring, which we call it as the potential energy. So this is how we calculate. How do you calculate the potential energy stored in the spring or energy change in the spring? That is the average force between the two positions multiplied by the displacement between those two positions. That will give us what is the energy change due to potential energy. I hope you have understood. Please each term. Kinetic energy translation along a straight line, half mx dot square. Kinetic energy because of rotation, half I into theta dot square. I is the moment of inertia of the rotating body about an axis about which the rotation is taking place. Okay, then potential energy change position mgh plus mgh or minus mgh. So here, so when you simplify this, okay, you can easily get it. Okay, let me simplify this. This is equal to, so k delta st plus k delta st. K delta st plus k delta st. That is 2 times k delta st. 2 times k delta. I want to separate it. 2 times k delta st divided by 2. That is nothing but k into delta st into x when I multiply it. Similarly, okay, k into x by 2 into x plus half k into x squared. Okay, so this is how we calculate what is called as the energy stored in the spring. I hope you have understood. Now I shall go for the application of this. Please remember the total energy. What is total energy? The sum of the kinetic energy plus potential energy. So what are the different forms of kinetic energy in the system? Maybe translation, maybe rotation, maybe, okay, these two. Then potential energy, the change in the position, this thing, okay. So this is what? The total energy is equal to kinetic energy plus potential energy. So now this I have expressions. So according to law of conservation of energy, what is the total energy? Total energy is always constant. So d by dt of, I want to differentiate the total energy. So as I know that this is constant, okay, what do you get this? This is 0. D by dt of total energy is 0. That is equal to d by dt of kinetic energy plus potential energy. You do this, you will get what is called as equation of motion. That is differential equation of motion. And observe it carefully, you will be able to write down what is called as the expression for natural frequency. Okay, this is what we are going to do. Okay, now let me apply this for spring mass system. This is the problem. Okay, again let me explain this. This is the spring, this is the free length, and I attach a mass. The mass will come down. This is the equilibrium position. Okay, from the free length now to this new position, equilibrium position, the spring has undergone certain displacement that I am calling it as delta st, and this delta st is equal to mg divided by k. Okay, so now it is the equilibrium position, the mass is stationary. Please remember, even now the spring is trying to pull it back. The spring wants to go back its free length position. Okay, what is that force? K into delta st. What is the force which is acting downwards? It is mg. That is why it is in a equilibrium state. Now I have induced the vibrations. Now the mass is vibrating like this. This is the new position. This is at T. At T equal to T, the mass is having what? What all things? It has undergone a displacement x. It is having a velocity x dot. It is not stationary here. It is still moving in the downward direction with a velocity x dot. And it is also having an acceleration of x double dot. Say in this direction. These are the things. Okay. Now with this, I would like to come back here and write down what is the total energy. Okay. Now this mass, the mass, okay, this here is possessing potential energy and also kinetic energy. So therefore, I shall write down what kinetic energy plus potential energy. So what are the different forms of kinetic energy? Do we have only translation or rotation or both? In this case, I have kinetic energy only due to translation. So only straight line motion is there, no rotation. Therefore, kinetic energy due to rotation is not there. Then potential energy. Potential energy. Do you have potential energy because of position? Yes. With respect to the equilibrium position, there is change in the position. Yes, there is change in the potential energy. Then is there any potential energy? Do you have a spring here in your system? Yes, I have a spring, and therefore energy is stored in the spring, and that energy also is potential energy. Okay, so now let me calculate what is kinetic energy due to translation. As I have said, half mass m into velocity square. What is velocity? X dot. X, please see here, x dot square. Okay, or then the potential energy due to change in the position. Change in the position with respect to the equilibrium position, the mass has come down. The mass has come down. Therefore, its potential energy has it increased or has it decreased? It has decreased. Therefore, it is minus. So minus mg into what is the height? What is the change in the distance with respect to the equilibrium position? So with respect to here, it has come down by how much distance? This distance is, this is the displacement, this is the distance covered, that is nothing but x. mgx minus mgx plus potential energy. Okay, with respect to the equilibrium position, it has come here. So during this time, how much energy is stored in the spring? That is nothing but the average force between these two, average force. So what is the spring force in this position? That is nothing but K multiplied by delta ST. The spring force in this position. And what is the spring force in this position? Plus K into delta ST plus X. The whole thing divided by 2. Why divided by 2? You have two forces, you want to take the average of the two. Multiplied by, what is the displacement between these two positions? The displacement is x. Okay, simplify this. This is equal to half m x dot square minus mgx. Okay, this k delta st plus one more k delta st, k delta st. Okay, or more I can do it. This is 2 times k delta st plus k into x divided by 2 into x. Okay, so this I would like to simplify. Half m x dot square minus mgx plus 2k delta st divided by 2. That is k delta st into x plus k into delta st into x plus kx by 2 into x. This is nothing but half kx square or kx square by 2. Okay, simplify this. mg is equal to k into delta st. So I am multiplied by x and x. This and this they cancel. So simplify this. This is what? This is equal to half m x dot square plus half kx square. Okay, this is what is the final simplified form. And what is the left hand side? The left hand side is total energy. I want to differentiate it. The rate of change of total energy, at what rate the total energy is changing. The total energy is not at all changing. And therefore, what will be this? This will be equal to 0. So what you have to do it? Differentiate these two terms with respect to, please remember, with respect to t. Okay? So I have to differentiate each term. What is the first? Half m is constant. Differentiation of what? Differentiation of x dot square. Differentiation of x dot square with respect to time. So first differentiation of x dot square, that is nothing but 2 times x dot. Then please remember, it is not final. I have to differentiate x dot now. Differentiation of x dot with respect to time. It is dx by dt already. Again d by dt. That is nothing but x double dot. Okay. Similarly, the plus half into k. Differentiation of x square. Differentiation of x square is 2 times x into the differentiation of x now. So what? When you write 2x, I have differentiated x square with respect to x. But my purpose is to differentiate with respect to time. Therefore, I differentiate x with respect to time. So differentiation of x with respect to time, what is that? It is nothing but x dot. So what is the left hand side? All sum of this is equal to 0. Okay, I can simplify here. This 2 and here in this itself I have one more. So similarly this 2 and this 2 I can say. And I shall divide throughout by x dot. 0 divided by x dot, that is nothing but 0. Here I have x dot divided by x dot. Then here also x dot divided by x dot. Okay, I have the equation. What is that? I shall write this and then equal to 0. So what is this? M x double dot. It is m x double dot plus k into x equal to 0. If you recall back, if you remember, this is the same differential equation which we had obtained. And we modified for the sake of writing the natural frequency x double dot plus k by m into x equal to 0. So therefore, omega n is equal to root of k by m. This is the expression for natural frequency. I hope you understand. Okay. So I don't think I will be able to complete the energy method in limited time. But I shall take it up in the beginning of my next lecture. I shall take simple pendulum and employ energy method and show that how we can get the natural frequency expression. Then I also take up by another method what is called as the Annix method, very simple one. We only, since it has been mentioned, I shall also discuss here and tell you how exactly we do it. But normally we don't use Rayleigh's method to get the natural frequency of a system. The most common ones are Newton's second law and energy method. Okay, so even D'Alembert's principle, that also is almost Newton's second law only. Therefore, Newton's second law is much simpler. We go for it, and this energy method. Okay, for simple systems, Newton's second law is sufficient. If the system is complicated, then you need to go for energy method. So therefore, these two we shall employ for more number of systems and understand that. Okay, all the best.